Okay, today I'm going to introduce our recent work about using GPU to accelerate inverse lithography towards high-quality curve mask generation. And this work, I'm the speaker, Haoyu, and this is also a collaboration with Mark Ren, or all from Media Research. In this talk, we're going to cover those three parts. Basically, some basics of computation lithography, includes lithography basis and the mask optimization background. And I will mainly cover the methodology following the cover design, retargeting, and mask rule check aware inverse lithography technologies. And I will show the experimental results demonstrate the performance of our approach. First of all, we're talking about the basis of computational lithography. Basically, this is kind of an important step that transfers chip design pattern onto the silicon wafer, which is a key technology in chip manufacturing. On the right-hand side figure, this is a sketch of the lithography system. Basically, you have the UV light source coming from the condenser centers, projected on the mask stage, and there will be light passing through the mask shape patterns collected by the objective lens, and finally they will be projected on the silicon wafer, forming the final design pattern. There are some big challenges in the lithography process because the extreme shrinking of the design, like in the 14 nanometer to 7 nanometer to node 3, they're not aligned with the lithography system, like the DUV or EUV, making the lithography process is a low-pass filter, and which means designs need to be optimized to compensate the distortion because of the mismatch between the light wavelengths and the design feature size. Here we're using the very simple and commonly used lithography modeling content that has been widely adopted in academia. It can be represented in the following equations where the area image, which corresponds to the light intensity projected in the silicon wafer, can be calculated in the following equations, which includes this big A, which is a transmission coefficient, and this is a masking frequency domain. And there are some of the approximation and speed up methodologies by using the SVD approach of applying SVD on A, and we reduce computing into this formulation. And finally, we also adopt this very abstracted resist model, just using the constant threshold to project the area image on the silicon wafer. Now talk about the inverse lithography. Basically, we have all of those equations, the modeling the mask pad, the design pattern on silicon wafer, its relationship and the mask design. And we want to formulate the IoT objectives. We want to minimize some objective which represents the difference between the wafer pattern and the original chip design. It will also need to satisfy all of those lithography numerical equations. Inverse lithography is part of the mask optimization story, and in literature currently there are two main streams of mask optimization methodology, which includes OPC and IoT. OPC itself is like a heuristic methodology that tries to move the shape edges inward, outward to compensate the distortion in the lithography system. And the IoT is leveraging the gradients directly from some kind of loss function and optimize the design in a pixel-based manner. All of those approaches currently have to honor the Manhattan geometric constraints because we are using this variable shaped beam mask maker because you have to like write the mask like a pixel by in certain shape by shape, one by one. And in this work, we're proposing the curve IoT because the recently the multi-beam mask writer comes in allows like a freeform mask manufacturing. And with this kind of objective, we are releasing the Manhattan geometric constraints into a simpler version, which comes with we measure the minimal width of the shape and the area of the shape, and as well as the curvature of the shape. From the concept itself, we can observe like OPC is super fast and LLT and also our curve LLT is kind of slow. But the curve LLT have the largest solution space because we no longer need to release the free-form mask into the Manhattan geometry. We'll talk about the challenges in the OPC and the IoT, and that we want to propose a solution to leverage the benefits of both. The consider mask rules during the optimization runtime is the first objective, and then we also want to release non-achievable objectives of faster and better convergence. First technique we want to introduce is the curve design retargeting. We already talked about that the lithography system is kind of a low-pass filter, which means the sharp corners, the Manhattan shapes in your in the post-physical implementation, all of those sharp corners cannot be manufactured, no matter how hard you try to optimize your mask, because the sharp corners will never be achievable by the lithography system. So, but in the past works, they didn't realize this fact, and over-optimize those corners will sabotage the whole process variations. I put some very simple example and draw a curve on some simple design. We'll observe that during the optimization steps, the gradient produced by the mismatch at the corner location of the shape will never change. So the optimizer will pay much attention on those corners, but never achievable. So this will definitely affect the convergence and the final results. And here is the example, with our curve design retargeting, we're able to reduce the gradient at corner location significantly. So it makes the optimizer focusing on the critical areas. The approach to the curve design retargeting is we want to round all of those sharp corners in the original design without affecting the connectivity, functionality of the original chip design. We are leveraging this so-called morphological operator, which are popular in computing graphics. There are 4 basic operators, which are called dilation, erosion, opening, and closing. From its name, it's kind of easy to understand. Like here, for example, here's a reference pattern. The dilation definitely pumps the pattern out, but the erosion removes part of those patterns. And opening and closing are combination of erosion and dilation, but in different order. We can see that from the figure that opening is actually round the convex corners of the chip design while leaving the concave corners still the same. And the closing is doing the opposite. So combining both the closing and the opening, we're able to round all of those corners in the chip design. And here's our algorithm, and we do the opening and the closing and combine all of them together, we're able to achieve the retargeted design. And we will use this retargeted design in the following optimization step. So here we want to talk about our assumption, using the about the mask optimization quality in curve era. So we're still focusing on the EPE and the process variation and also the mask smoothness. Those 3 terms can be achieved in our newly proposed cost function. For the first 2 terms, they're still the same as in the past. We have the EPE, we want to minimize the error in nominal condition and also want to optimize the process variation. The important thing comes from the 3rd term. We know that the mask should be smooth enough and does not have lots of defect, artificial defect validating stuff in the final mask. Our observation is that all of those stuff are actually high frequency components in the mask. So we want to minimize the high frequency spectrum of the mask in this term. We take the Fourier transform of the mask and take the modes greater than k, and we want to minimize this term. So the final results will be even more smooth. For the remaining 2 items about the shape area and the shape distance, which is the assumption we used when we're targeting curvilinear mask, we still leverage the morphological operator, but in our case, we implement all of those stuff in a differentiable manner. Actually, those can be easily achieved with basic PyTorch operators, and which are enhanced plug and play for any GPU accelerated IoT algorithm. The intrusion, first of all, the intrusion tries to remove the artifacts, smaller artifacts generated during the IoT stage of the dilation merge the closed shift, where there will be like a small channel in the path in the per algorithm, but with the help of dilation, they can merge them. Because all of those are differentiable, those can be directly implemented in the GPU accelerated IoT, and all of those happening during the optimization runtime. So we can save time for the post-processing, like the per work have been doing. And this will also preserve the optimality of the whole IoT results. Next, we're going to talk about the experiments. Those the data set, we have two group of data sets. One is a very popular SCAS13 context data set. It contains like 10 toy examples with 10 to 20 shapes in each clip. And we also have this a larger data set which calls the Lethal Bench. It's published in NeurIPS 23 dataset benchmark. And here's a link of this benchmarking, and it contains a large collection of mental via clips for ML purpose. But we only take the testing clips extracted from standard cells. So it only contains like hundreds of clips we use in this experiment. Next, we're going to talk about the experiments and comparison with the SOTA results. For the ICCAS13, we can see our results achieve the best EP evaluation compared to all previous work, DAC22 and DAC23. And similarly, for the Lethal Bench, we also achieved the best AP results. It should be noted that we also have very good numbers on the mean ship area and the mean ship distance, which are good indicator for the mask manufacturability purpose. And we also show the runtime of our approach, like we also achieve the best throughput compared to the previous work, because we have this curve design retargeting, and we facilitate the convergence by a lot. And next, we also want to show some of the claims in our paper. We're talking about the side effects of post-processing. We re-implement the DAC23 paper by ourselves, and we run all of the experiments. We try best to reproduce the results of that work, and we did the post-processing on the final optimized mask. We're seeing that post-processing will increase EP relation by 20% and also the MIC number by 5%. So this is a demonstration of our claims about the side effects of post-processing. And in conclusion, we propose this fast GPU accelerated IoT algorithm, and we have this curve design retargeting allows faster and better convergence. We also introduced a differentiable morphological operator that eliminates rule validating artifacts during optimization runtime, which avoids post-processing. And lastly, we're undergoing internal process to release the source code, and you can follow this GitHub link, and that code should be ready anytime.